Hello and welcome back. Today I want to talk about antennas and how they can be modeled in a circuit simulator. This is quite a complex topic, so to aid in today's discussion, I will be performing the actual circuit simulation using LTSpice, but to extract the antenna parameters, I will also be using the mmana-gal antenna simulation software. So if you're curious, then keep watching. Now, any piece of wire could be called an antenna. If you've ever worked on EMC or interference issues, you will probably know that every single trace on a PCB can behave like an antenna, regardless of whether you want this or not. So it will not necessarily be a good antenna, but it will function just well enough to give you a few gray hairs. And at the end of the day, an antenna is just a passive component that can turn an alternating current into an electromagnetic wave, or the other way around, it can take an electromagnetic wave and turn it into a current. So the antenna is a bidirectional transformer. And because of these two distinct behaviors, the antenna is usually treated separately when used for transmission compared to when it's used for reception. So let's start with the transmission use case. As a passive component used in an AC environment, the antenna is characterized by a complex impedance. It has a real resistive part and an imaginary reactive part. The resistive bit can be further decomposed into two distinct behaviors: the loss resistance and the radiation resistance. So the useful electromagnetic wave that gets generated by the antenna takes the energy dissipated by this radiation resistance. Whereas for the other parameter, the loss resistance, well, the antenna itself is built from real materials, real lossy materials, so the loss resistance is highly dependent on what the antenna is built from. And the energy dissipated on this is wasted in the form of heat. This separation is important since this shows that even if you have a perfectly matched system, your antenna efficiency will be limited by the loss to radiation resistance ratio. Finally, the reactive bit can have an ideal value of 0 under special cases, like a half-wave dipole or a quarter-wave monopole, but in every other case, you will get some reactive element, either capacitive or inductive, based on the antenna geometry and the test frequency. So at this point, you might be thinking, okay, the antenna is modeled as a two-terminal component, but I have a single wire. Where does the other terminal go? Well, here we have two main cases: balanced and unbalanced antennas. You will always get the two-terminal model, it's just that the second terminal is not always obvious in a poorly implemented antenna. So with a basic balanced antenna, like a dipole or a Yagi, the two terminals of the antenna are the two terminals of the dipole. Because the current going into one terminal creates a field around the antenna and then comes back through the other terminal. In an unbalanced antenna, like the monopole or ground plane antenna, one terminal is the obvious antenna bit, and the second terminal is the ground to which the field closes back. Now, in a less obvious structure, like a PCB antenna from a wireless device, the second terminal is again the ground, but it's the ground system to which the field from the antenna closes back. In this case, it's not a very clearly defined point, rather it's a larger area. That, from a layout point of view, needs to be prepared for this specific purpose, so that you can get the best results. So this shortly covers the transmission antenna. What makes the reception case so special? So a complete antenna model for reception can look something like this. You have your two resistive bits, the reactive bit, and then you have the incoming signal, and then a noise source. This can be further detailed if needed. Now, this noise can come from the environment, but also from the construction of the antenna, namely its resistance. The significance of taking into account the noise becomes apparent when observing the signal-to-noise ratio. If you ignore the noise, it does not matter what impedance the antenna has, since you can always perform matching and half of the input signal will reach the receiver. With the noise modeled, it becomes obvious that the larger the resistances of the antenna are, the more noisy it becomes, since the noise is directly linked to the resistance. Now, before we can start simulating, we need some values for the components that model our antenna. depending on your application, there are some special cases where you know the exact expected impedance, like a resonant dipole has 73.1 ohms of radiation resistance and no reactive bit. But what about the case when you don't have a clear answer? Well, certain basic antennas do have some simple estimation formulas, like the electrically short monopole or dipole, and alternatively, you can measure the antenna using a network analyzer, but you need to build the antenna first for that. Or you have the option to use antenna simulation software. There are multiple ones out there, but for today I will be using the free version of the mmana-gal software. So this is a program in which you can model antennas from straight lines. At the moment, I'm using the 160 meter dipole as an example. But if you're curious, there are a lot of examples that the program comes with that you can play around with. Anyway, after defining the antenna structure, you can view it. Now, with a single dipole, there's not much to look at. But anyway, once the antenna structure has been defined, you can proceed to calculate it. You can define a test frequency, and the program will tell you what is the complex impedance of the antenna, as well as some other information at this frequency point. So here, if our reactance is positive, the antenna is behaving inductively. If it's negative, it's behaving capacitively. And based on the antenna material, we can determine our radiation and loss resistance. So with a lossless material, we only have our radiation resistance. And if we select some other material, say aluminum wire, then the difference between the two resistances will be our loss resistance. Now, for whatever reason, the reactance is also being impacted by the material, but it doesn't change all that much, so that's okay. So one of the use cases of this program will be to evaluate your antenna structure under various conditions. So this way, we can get the single frequency behavior, which can easily be converted into an electrical model. Now, your antenna will most likely be used over a frequency interval though. So if you're a ham operator, you will use it in a specific ham band or over multiple bands. So how will the antenna behavior change with frequency? Well, we need to go back to the simulator to find out. So in the program, if we go to the plots menu and to the far fields setup, we can select all points, and the program will calculate our impedance at multiple frequency points. So the center frequency will be the frequency at which we started off with, and then the other points will be determined by the bandwidth that we've selected. So by doing this, you can observe how the antenna impedance changes with frequency. Both its resistance and its reactance will vary based on the test frequency. Now, this information can now be transferred into LTSpice into an AC simulation using the FreeQ function. And if you need more than 5 points, you can simulate at different center frequencies or with different bandwidth selected, and then just combine all of the results. So, to transfer the simulation data to LTSpice, we can make a resistor model that has the impedance characteristic of the antenna that we've just simulated. The only thing to keep in mind though is that the model will require admittance, which is the inverse of impedance. So first thing I had to do was take our impedance values and invert them before processing them and putting them into the format that LTSpice needs. So for this I used Excel, but any spreadsheet program or manual calculation will work just as well. And then I put everything into a sub-circuit model. So this resistor is not really a resistor, it's a sub-circuit which uses this attached model. So now if we run the circuit and just divide this voltage by 1 ampere, we have our impedance characteristic of our antenna. An antenna that is resonant at around 1.82 MHz. So this model will be usable in an AC type of simulation. Now, if you need an RLC equivalent circuit, something that can be used in a transient simulation, based on the simulation data, you can make an approximate circuit. First, based on the response shape, you can determine the equivalent circuit. Your antenna is either behaving like a capacitor or like an inductor. And whether you're close to resonance or not will determine how complex the model needs to be. And now, to figure out the exact values, for the reactive bit based on some extreme impedance points, you can create two equations. and determine the equivalent capacitance and inductance, which will give the same response. For the resistive bit, you have a bit of a problem. The resistance is not a constant. So here you can just take one of the resistance values, either one of the extremes or an average, and just live with that. And then, based on the ideal real material simulations, this resistance value can further be split up to account for loss and radiation. So after doing a bit of calculation, we can create our RLC model. For the resistance, I split it up into radiation and loss resistance, based on the difference between the resistances obtained with a ideal and a real material. And then for the reactances, I took the extreme reactance points and calculated the equivalent inductance and capacitance. So if we now run the simulation, we can compare the results from our initial model and this one, and we can see that they are very, very close. So you do get differences. We are not modeling the frequency-dependent resistance, but this new model will now be usable in a transient simulation. Now, if you do need a more accurate model, you can always create single frequency models. So just take the impedance value from a given frequency and model that. And the model will then be valid for that specific frequency. Now, if you do have a practical antenna already built and you have a network analyzer lying around, you can always measure it. You can extract the S11 parameters and simulate that. I covered the method to use S11 parameters in LTSpice in more detail in a previous video. Now, if you do end up doing this, there are some measurement considerations to keep in mind just to get the best results. First, as with any good network measurement, the system needs to be calibrated. So right now it's showing the 50 ohm termination resistance response, and in case the measurement point is not the same as the antenna point, for example, if there's a cable in between the actual antenna and the measurement point, this needs to be compensated for. And the other thing to keep in mind is that the antenna impedance is highly dependent on the environment around the antenna. So this is a ground plane antenna that I previously built for the 70 centimeter band. If we connect it to the network analyzer, we can see that at around 436 MHz, it has around 53 ohms of resistance and 0.7 something milliohms of reactance, but the exact value will highly depend on what is around the antenna. So now if I have my hand closer to it, its reactance increases. If I hold it at a slight angle, again the response changes. If it's somewhere higher, again we're getting a different response. So the point is that if this sort of network measurement is giving you a different result than what you were getting from the simulation, the problem is not that the simulator is wrong, but rather the environment in which you're simulating and the environment around your practical antenna are not always the same. So it's perfectly normal for differences to appear. In the end, antenna modeling can be a useful tool to confirm the expected circuit operation. Maybe you're interested in the impedance matching, your actual output power, or you just want to see what sort of performance you should get. Sometimes you will be able to obtain the antenna parameters from calculations, but in today's age, it's always easier to just simulate. And with that said, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to get updated on my videos, and see you next time. Bye bye.